Hey guys, and welcome back, and this week's video is going to be about the SINE rule, what it is, when to use it, how to use it, and a proof of it. So let's start off by what the SINE rule is. Basically, what the SINE rule claims is that if you have an angle, and you divide the sine of that angle over its opposite side length, that will be equal to the sine of each angle in that triangle over their opposite side. So whilst that might sound a little bit convoluted, what I'm trying to say is that if we have an angle A and the opposite side is defined as its side length A, we're going to have that the sine of that angle over that opposite length is going to be equal to this angle right here, the sine of this angle over the opposite length, and the sine of this angle right here over its opposite length. And this can be seen in this equation right here. So take a moment to look at it, to understand it, and then let's do a couple of examples to see how that actually works. So our first example, let's focus on this one right here, is when we have an unknown side length. And we know that in a triangle, we have 40 degrees, 95 degrees, a side length of 8 centimeters, and our unknown side. And what we can do is using this equation right here, we can set up an equation to solve for x. So we know that the sine of 40 over x is going to equal to the sine of 95 over 8. Now what else is to know is because this is a fraction, you can turn this around. You can have that a over sine of a is equals to b over sine of b is equals to c over sine of c. You can just do a little bit of quick algebra to see why that totally makes sense. And then, because our unknown is x, it's easier to put the side length in the numerator. So we're going to use this form of the equation right here. And we're going to say that x over sine 40, the opposite angle, is equals to 8 over sine 95. And if we solve that by timesing everything by sine 40, we're going to get that x is approximately 5.16 centimeters. Now let's move on to the second example where we have an unknown angle. We know that two side lengths, one of which is 12 and one of which is 8, and we also know an angle of 88 degrees. And again, it's important that we know the angle and its opposite side and that our unknown angle has a known opposite side. Now in this case, we're going to use this form of the equation simply because then we can have an unknown variable in the numerator and it's easier to work with. And we're going to see right here that sine of theta over 8, opposite, is equal to sine of 88 over 12, again the opposite side. And we times everything by 8 and take the inverse sine of that, which is what we're doing right here, to get that theta is approximately 41.8 degrees. Now, just looking at these two examples and looking at this equation, when do you think we apply the SINE rule? Obviously, it's applied to non-right triangles, as we have seen, but what should we know and what do we have to find in order to apply this rule? Well, if you simply look at the variables, if you want to know and if you want to find one variable of the equation, what are the knowns that you have to have? Well, you can know two side lengths and an angle to find a missing angle, or you can know two angles and one side length to find a missing side length. And these are the two scenarios that we generally use the SINE law or SINE rule to solve. So when we have two angles and one side and we have one unknown side that we want to find, or when we have two sides, one angle, and one unknown angle that we want to find. So in this case right here, we had an unknown side, two known angles, and one known side. In this case right here, we had an unknown angle, two known sides, and one known angle. Now, let's look at the proof for the SINE law. And it's actually quite simple, but it's very elegant and concise nonetheless. And what we do, basically, is before we have worked with sine and cosine in right triangles, and we know what sine and cosine are in right triangles. Now that's kind of hard to apply to a non-right triangle because there's no hypotenuse, so what are you going to be dividing your sides by? But we can get ourselves out of the situation by always creating two right triangles within a non-right triangle, as we have done right here. So let's focus on this triangle first. So again, we have defined our angles as letters and the side lengths as the same letter but opposite to that angle. So C and C, or B and B. And first, let's start off by doing what we know. We know how to find the sine of these angles. And sine is opposite over hypotenuse, so SOHCAHTOA. So sine B is going to be opposite, which is H over hypotenuse, which is C. So it's going to be H over C, which is what we have right here. Then sine of C is going to be opposite H over hypotenuse, B. So H over B, which is what we have right here. And then we can rearrange both equations so that we express H in terms of C and B. And this is what we get. Just times everything by C in this case, or B in the second case. And you can already see where this is going. Basically, we now have two equations that equal H1, so they equal each other, as we see right here. So we know that C sine B, therefore, is equals to B sine C. And if we divide each side by B and each side by C, we're going to have that sine B over B is equals to sine C over C. And this is very simple, but we already have it. Well, what about A, you might ask? Well, that's exactly what we're going to do next. See, this triangle doesn't really do much for A because the height cuts the angle of A and we can't work with it. So that's why we have to draw a second triangle. And this triangle might look a bit confusing, but all I'm doing here is creating a triangle that looks something like this, where this is the right angle, this is H2, this is A, this angle right here is A, and this is C. So C is the hypotenuse. Now, what is the sine of A? Well, it's opposite over the hypotenuse, so it's H over C. And another angle that we have right here that we can use is C. So sine C is going to be opposite over hypotenuse, so H2 over A. And again, we repeat what we did last time, and from each of these equations, we express them. We express H2 in terms of C and A, and we get that C sine A is equals to H2, whilst A times sine C is also equal to H2. So C sine A is equals to A sine C. And just like we did before, we divide everything by A and C to get that sine of A over A is equal to sine of C over C. And because we know that sine of C over C is equal to sine of B over B and is equal to sine of A over A, we now also know that sine of B over B is equal to sine of C over C is equal to sine of A over A. And we usually arrange it in alphabetical order, but obviously that doesn't really matter when it comes to mathematical truthness because this is still the same equation. And like I've said before, because these are all fractions, you can simply flip them all around to get that B over sine B is equal to C over sine C is equal to sine of A over A. Just think about having everything right here over 1. So 1 over sine B over B is equals to 1 times B over sine B is equals to B over sine B. And if you do that for every single part of your equation, which is what you always do if you have an equation, you're going to get this right here. So this is our sine rule and its proof, which is pretty simple, as I've said, but very efficient. And I hope you enjoyed this video. I hope you know when to use the sine rule. I hope you understand how to use it. And of course, I hope you understand what it is. I hope you learned something new, and see you next week.